Now I will give a very short introduction to groups and group actions, which we will need when we are discussing Polias theory of counting. Most of you must be familiar with groups. In case not, here is a very short introduction about it. So a group is basically a set with a binary operation like addition or multiplication, and such that the group, the set is closed under this operation, right? So all the pair of elements under this operation gives rise to elements in the same set, and it satisfies the properties like associativity, and it must have an identity element with respect to the operation, and every element has an inverse. So if these properties are true, then the set together with this operation, binary operation is called a group. So what is associativity? Like for any three elements in the set G, X, if star is the operation, X star of Y star set, right? So you take the operation Y star set, right? The element corresponding to that, and then with respect to X and Y star set, you do the operation again. What you get is must be identical to, must be the same element as you first do X star Y, and then take star with set. Right, so this is associativity. Then you have the identity element that if you apply star with this identity E, then X star E is equal to E star X for every equal to X for every X, and for the identity element E. So you should have such an identity element, and then if you take any element in the group G, then you can find an element which is called the inverse, where if X is the element, then Y is an inverse of G, inverse of X. If X star Y is equal to identity, and that's also equal to Y star X. Okay. So any element commutes with the identity element. This is another fact. So if all these three properties are true, these are called the group axioms. So if all these three properties are true, then what the set is a group with respect to the binary operation that we have. Now, several examples of group occur naturally. In fact, all these ideas actually come from the everyday mathematical objects like natural numbers or integers and all we are considering, right? So this idea comes from the usual mathematics that we do. So we can find several examples of this. So we will see some of them soon. So a group has, so I mentioned this before, the group has a closure property that any two elements, if you take, then with respect to the operation star X star Y also is an element of it. Okay? Now, if any two elements have this commutativity, that if X star Y is equal to Y star X, then the group is called abelian, or it's a commutative group. So, as I mentioned, Z, the set of all integers with respect to addition is a group. So we call it an additive group, where 0 is the identity element, right? If I take any integer and then add 0 to it, it does not change, right, value. And you can add a number with 0 or 0 with a number, you will still get the number that you started. Then you have, for any number, it's negative, right? Is the inverse that you know. And it is also commutative, right? So because x plus y is equal to y plus x for any two elements. And other examples that occur naturally are the set of rational numbers, set of real numbers with respect to addition, right? Set of complex numbers. So all these are additive groups. So we have several natural examples. Then there are multiplicative groups because the binary operation can be multiplication instead. So if you take the non-zero rational numbers or positive rational numbers with respect to multiplication, it forms a group with respect to multiplication, and where one is the identity, right? It's a group with respect to multiplication, and it's also abelian again. Multiplication in our natural settings are all usually commutative. Then you have the positive real numbers with respect to multiplication with it's also identity. Similarly, if you take all these Q, R, C, etc., and look at just the non-zero element, that also forms multiplicative groups. Right? So Q minus 0, singleton 0, R minus singleton 0, and C minus singleton 0 are all groups under multiplication. Now, other than this, we have finite groups. For example, minus 1 and 1, right? They form a group with respect to multiplication. And because any two elements, if you multiply, it belongs to the set itself. Every element has a multiplicative inverse, which is itself, right? And then you have the identity element, which is 1. So you have all this associativity that I can verify. Then you have 1 minus 1, I minus I. This is also, right, is a subset of C, right? Because I and minus I are complex numbers. This is also an example of a multiplicative group. So we can verify all these things. So I insist, if you are not familiar with groups, you should work out this, try to verify each of them is actually a group with respect to the operation that we are discussing. Then another example is the numbers under modular arithmetic, right? Positive natural numbers. If you take any positive natural number n, then you can look at the numbers 0, 1, 2, etc. N minus 1. And this set, we should usually denote by z subscript n, is the group with modulo arithmetic, where we are looking at the modulo n arithmetic, right? So whenever I add numbers, right? So the addition is with respect to so if I take x and y, then x star y is x plus y modulo n, right? So you look at the remainder when divided by n. That's what this is. So x plus y, right, is equal to x plus y if x plus y is less than n. That is the definition. And x plus y minus n if x plus y is greater than or equal to n. And one can show that this is actually the modular arithmetic. So now prove that the group properties all satisfy for Zn. And this you should take as a homework and then do it. One can show this easy. Now, a very important group that we will come across many times in the next few lectures is the symmetric group. So, symmetric group is the set of all permutations of a set. So, take any set, look at all possible permutations of the set, then this forms the group of symmetries or symmetric group. So, why is it called symmetric group? Is because if you take, for example, combinatorial objects which also have some geometric representations like polygons or higher dimensional polytopes or things like that, you can define certain symmetries of this. For example, symmetry under rotation, symmetry under reflection, and these kind of things. And all these symmetries can be represented in terms of permutations of the either vertices or faces. And therefore, one can see permutations themselves as as a kind of symmetry. and it just depends on what we want to consider as a symmetry or not. And therefore, set of all permutations is called a symmetric group. Now, if you take any set X, then Sx is called a set of all bijections from X to X, which are the permutations. And we define for any two permutations in Sx, the composition F composition G is F of G of X, right? So G of X is basically the map of X under the permutation G. Then F of G of X is the map of map of G of X under the permutation. So therefore, one can show that F0 G or F composition G is also a permutation, right? One can show this. You can take it as an exercise if you want. And similarly, one can show that this composition is basically associative also. Now, if E is the identity map, right? Because any element is not to itself is the identity, then E is an identity for the symmetric group as well. So one can show this by taking E composition F is equal to F composition E, and it's actually equal to F. It's again trivial to verify, immediate. Then we have inverse, right? If you take any permutation, then you can also find the inverse permutation, so that the composition gives you the identity permutation. And again, that the inverse permutation will give you the identity permutation when you compose it with the F that you started with, and one can verify this. So I request you to go through this and then verify this to be the case. Now, as we mentioned, Sx is called a symmetric group. Now, if X is a finite set, let's say 1 to n, then Sx is usually written as S subscript n, because it's the nth symmetric group. Then show that as a homework. In general, Sx is not commutative. Okay? So, because most of the natural examples that we saw earlier were all commutative. Now, let us look at some group which need not be commutative. So, here is Sx, set of the symmetric group, set of all permutations of a set, and this need not be commutative. Then as homework, you can show that the identity element is unique in the group. Again, this is quite fairly easy exercises. Then for any element, its inverse is also unique, right? So the group has these two properties, that it has inverse for an element and there is an identity element, right? So show that these are unique. Then once you show this, you can show the cancellation laws. So the cancellation laws are the following: that if let's say A, X, Y are elements of the group G, then Ax is equal to Ay implies X is equal to Y, which means that we have the left cancellation law. That if the left side of in an identity, right, where you have multiplication by the same element on the left, then you can cancel that. Then similarly, we can show that Xa is equal to Ya, right? It implies X equal to Y, again the right cancellation law. And the inverse of the inverse is the element itself. X inverse whole inverse is equal to X, and Xy whole inverse is Y inverse X inverse. This all holds for arbitrary group. If the group is commutative, of course, Xy is equal to Y, so you can write it differently, but otherwise, we have this true for every group. Now, the proofs are again very simple. So, the first one, Ax is equal to Ay, multiply by A inverse on the left. Then you will get A inverse Ax equal to A inverse Ay, right? This one can do. And then, therefore, A inverse A is identity E, and Ex is, of course, X itself. So, Y is itself for X equal to Y. So, that gives you the cancellation. And similarly, 2 follows from the right cancellation also. And if you want to show x inverse whole inverse, what you do is you take x inverse whole inverse and multiply with x inverse, right, on the right. Then by definition, it is the identity, right, because the inverse of an element itself is the identity. But now that is x inverse, right? This is true, right? Then you can use the right cancellation law, right? X inverse is on the right side of both, so right cancellation gives you x inverse inverse must be equal to x. Similarly, you can show the fourth one also. I leave it as a homework to do. Now, when you have an element multiplied with itself several times, that is right. Then we write it as uh, x to the power of n if the group is multiplicative, and the operation star is additive operation. Then we can also write it as nx whenever. In rare cases, I mean, one also writes group using the multiplicative notation, right? The additive groups also. Sometimes it is easier to discuss both cases. In that case, one can use the multiplicative notation for the additive groups as well. But we will not worry about that. We will not go into that, I think, at the moment. But in this case, we can just say that, okay, if star is multiplicative, then n times x star, etc. is written as x raised to n, and it is additive, then you write it as n times x. This is the natural way to see this. Now, a subgroup of a group. So, given a group G and a subset, let's say H of G, we say that H with respect to the same operation star is a subgroup of G if H with respect to star is a group by itself. So H is a subset of G and H comma star is a group by itself. So then we say H is a subgroup of G. So examples are, for example, Z comma plus, right? So the integers with the addition is contained in the rational numbers with addition, and we know that it is the same rules of addition that we use. And in Q, right, we see that set is just a subset with the same addition. It forms a group by itself. Therefore, it's a subgroup of Q plus. Now, Q plus is sitting inside R comma plus because again, real numbers with respect to addition contains rational numbers with respect to addition. As a subgroup. Then Z is a subgroup of both Q as well as R, intermediate, and Q is a subgroup of R. This is what we saw. Now, a subgroup is said to be normal. We probably will not need too much of this in this course, but just for completion, we just mention this. So, a subgroup is normal if for every group element G of G and every element H of H, G inverse is an element of H. Now, if you look at any abelian group, one can show that the subgroup of abelian groups are all normal subgroups. So this you can take it as a homework and show why it should be the case. If G is abelian, then every subgroup of G is a normal subgroup. That will give you several examples as well. So work on this and try to come up with a good examples. Now, given a group G, you can take an element, and then as we did before, we can take the powers of this element, right? You can multiply it with itself or add it with itself, right? Either way. And then you can do this several times. Then you look at this x raised to n, right? For every natural numbers, in every integer in Z, right? Because we can also define the negative power because it's basically uh, uh, you can look at the whole of whole of Z under this operation star, right? So x raised to n for n belongs to Z, one can show is the subgroup of G, right? If you take an element and multiply with itself, if you are or look at the powers, like whenever n is 0, for example, you will get the identity, and whenever n is other numbers, you will get the numbers in the group itself. And this forms a subgroup because it is always staying within inside. And one can see that this is a group by itself because this for any number you can find an inverse, because if I take x raised to n, x raised to minus n is an inverse, right? Because x raised to n times x raised to minus n is x raised to 0, which is e. This you can verify, and then if you have a subgroup which is generated by the single element, it's called a cyclic subgroup. Now, any group which is generated by a single element is called a cyclic group, and therefore such a example shows that every group has a cyclic subgroup. Because you take any element, multiply with itself, right? Find x raised to n for every n. You will get what you will get the subgroup which is cyclic. Okay? And x raised to minus n can be defined by taking as the inverse of x raised to. Because to identity, if you look, that's precisely what you are going to get. X raised to 0 is e, and therefore you can solve this. Then another concrete example is Z plus is generated by 1 itself, right? 1 you can add, with respect to addition, you can find the inverse, etc., and then you have the whole of Z generated by the single element 1. Therefore, 1 is Z is generated by itself. Therefore, Z is cyclic. Z is also generated by the single element minus 1, right? Therefore, it's generated by two of these elements. Now, Kz for any k is a cyclic subgroup of Z, because when you have k larger than 1, then Kz will only give multiples of k, and this forms a additive subgroup which is also cyclic, because you can see that Kz is generated entirely by k. And if you add any or two of them, you will get again an element of the type Kz. So one can solve this thing, and then show that rational numbers, right, q with plus is not cyclic. This is another nice example, nice exercise. Now, what we want most is the group actions. So, what is a group action? So, consider a group G. Okay. Now, X be any set, then we can say that the group G acts on the set X by way of the following function, right? So, G, so you will define a function, let's say dot, which takes G cross X, right? The Cartesian product of G and X, right? G cross X to X. So, these pairs of elements, so you take the element from G and then element from X. This pair is mapped to some element of X, right? So, basically the elements of X are being permuted by the action of the group, right? Because elements of X can be mapped to X by the action of elements of the group G, right? So if G has G1, G2 as elements, then G1 will take some element, let's say x1 of X to some y1. Then it can take x2 to y2. And then G2 can take x1 to y2 maybe, right? And x2 to y3 or something like that. Right? So this way we have the group which acts on this. Now, when do we say that this function defines a group action. That is only if for every group element and for every element of the set X, we have g dot x as an element of X, right? So the function must take elements of X to elements of X, and every element of X with respect to the identity of the group must produce it. So identity of the group cannot take element to anything else. So it should take element to itself. Then for any two elements of the group G and H, right, and any element of the set X, the product G dot H of X, G dot H dot X is equal to GH of X, which means that if you apply S to G, S to X, right, H takes X to something, then you take that whatever that element which is also in X, you apply G, right? It is the same as you do the action of, you do the operation of G and operation of the group G to G and H. So GH is the group operation, G times H, right, or G plus H, whatever it is in the G. So GH is an element of the group, right? So GH gives a new element of the group G. That element, if you take the, if you act it with the X, then that should be the same, right? So applying H followed by G is the same as applying G and H, taking the product of G and H in G, and then applying the X. So if these three properties hold true, then we say what we have defined, the function is the group action. Now, some examples here. So if you take any set X, the group of symmetries of, right, the permutations of elements of X, of course, naturally acts on X, right? Because any element of Sx is just a permutation of the elements of X, and we know that the product of permutations is a permutation, right? And then one can show that all these three properties holds true, right? So if you take the first property says that we want for every G in G, for every X in X, G dot X must be in X. Now G of X belongs to X for any G of X belongs to X for any permutation G, and then because of this, we have this first property, right? Gx belongs to X. Then the second property holds. What is second property? Second property says that for every X in X, the E identity, then E dot X must be equal to X. Now that is true because E is identity permitted, right, of X itself. So therefore, this is true. Then third one holds, which says that the composition must be also true, right? So G of H dot X is basically G of H of X, because H of X is a permutation of X. Then G of H of X is the permutation of H of X. And this, by in permutation, we know that the composition has this property, right? Therefore, G composition H of X is also equal to GH of X, because GH is the composition of G and H in the symmetric group. This one can show to be easily true. So all these three properties hold, and therefore the symmetric group acts on the set. So this is our most important example, because one can show easily that any group action can be represented by action of a symmetric group. Okay. So if you take a group G and a set X, then let us define G dot X as GX G inverse for elements of GG and element of XX. Now this is a group action. So this is the claim, and I want you to show that all the properties of the action, right, all the three axioms holds true in this case. So this is a very good example. I want you all to try this. Now a remark that any group action of G on X has a permutation representation. I just mentioned this before. as a homomorphism from G to Sx. So I want you to think about this. This is not very difficult to show, but I am not going to work out the details in this short introduction. But it would be nice exercise to try, and if you have any difficulties, get back to me. Now, another important notion that we want is the what happens under the action of a group, right? So to an element, what happens, that is represented by the idea of an orbit. So take elements of the set X and see what happens to the elements under the action of the elements of the group G, right? So take all the elements in the group G, see where it takes a fixed element of X, right? So if small x is an element of the set X, then Gx denoted by G followed by X is basically the set of all elements G dot X, right, where G is an element of the group. And this is of course a subset of X because Gx takes elements of X to elements of X. Right? So therefore, it's a subset of X, and this is called orbit of X. So for a fixed element, its orbit is all the other elements, right? All the including except all the elements of X that are to which X can be taken by the action of G. Now, here is a concrete example. Let X equal to A, B, C, D be the set, and G is the group which is Z2 cross Z2, right? Which is basically 0, 0, 0, 1, 1, 0, and 1, 1. Right? Now, let us see what happens to ABCD under this action. So, we are going to define an action. So, G act on X as follows: 0, 1 takes A to B. Okay, 0, 1 is just an element of G. It takes A to B, and it takes B to A. And similarly, 0, 1 takes C to C, and 0, 1 takes D to D. Now 1, 0 takes A to A, 1, 0 takes B to B, 1, 0 takes C to D, and 1, 0 takes D to C. Now, I have not defined what 0, 0 does or 1, 1 does, but since 0, 1 and 1, 0 can generate the whole of G, you can show that this also defines the other actions, right? What happens when 0, 0 acts on A or 1, 1 acts on A, etc. So this one can verify. In fact, you should verify, right? What happens to this? And then once you have all these things, you can show that the orbits of the action are A, comma B, and C, comma D. Now A, comma B. So A is always taken to B, and B is A is taken to either A or B, and by the elements of G, and B is taken to A or B itself. And similarly, C will be going to D or C, and then D will be going to C or D itself. And one can verify that A never goes to C or B never goes to D, etc. Right? So these properties one can verify. Now, yeah, and you should check out all these. Now then, as a homework, you can do the following. If G is a group acting on a set X, for two elements X and Y in X, let X tilde Y, right? X is related to Y, if and only if Y is G dot X for some group element G, right? So if Y is in the orbit of X, right? Now show that this relation is an equivalence relation. In fact, if Y is in the orbit of X, then X is also in the orbit of Y. Is an equivalence relation, and hence show that the orbits partition X into disjoints, because equivalence relation partitions the equivalence classes basically form a partition of the set in which it is defined. So therefore, one can observe or one can show that the orbits are basically the equivalence classes under this equivalence relation that we have defined. and hence they basically partition the set X to disjoint sets. And this property is very important. We will use it quite often in the next few lectures. Now, given a group G and a subgroup of G, let's say H, we can let H act on G, right, by left multiplication, right? So you take the subgroup H, then act on G by left multiplication. So we are looking at elements of H with multiplied to elements of G, right? So X is an element of G and H is an element of H. Then H dot X is written as just HX, which is the which defines the left multiplication. Now, this left multiplication by H, one can show that it's actually a group action, and show that it is a group action by showing all the three properties holds, and then define the and then find the orbit of an element, and this orbit of element which is basically hx that we defined earlier, right? We denoted by gx, right? The action of g on the set x with the element x is going where, that is the orbit of x, right? So hx similarly defines the orbit of x under the action of h, and this is the set of all hx such that h belongs to h, and this is called the right coset of x with respect to the subgroup of subgroup h. So this idea of cosets are also important. Okay? Again, cosets come from the group actions, but it has independent importance as well. So we will see this. And as a homework, I want you to try out and show that if H is a subgroup of G, then order of H divides the order of G. This is very immediate once you show these properties that you can show, and show that this is an equivalence relation, etc. And one can immediately show that this is actually the true, right? This is a very famous result, right? Order of a subgroup divides the order of the group. And with that, we can stop this very short introduction to groups and group actions. We will need a few more things, but that we will introduce when we discuss Bolyai theory